there a connection with SDSU?
Sorry? Yeah.
Can you hear well?
Yeah, I can hear you.
Okay, good. Well, thank you all for excellent presentations last time, and I think it was a very nice activity, and I hope that we helped each other by looking to presentations made in the class. So we should keep going forward, and our course will contain several chapters, and some of them will be connected with ionic parts, with positions of ions, and some of them with electronic structure. So before we go forward to the precise treatment of electronic structure, we need to know where the ions are placed. So we need to, we are still at the introductory level. We need to get an idea how to get an ideal optimal position of ions. And we are going to review some algorithms, how to get those positions of ions. So, well, this statement is wrong. There is a handout number, I think 5 on the D2L. And if you're interested, please look on it. And I'm going to change it to erase the one that is on D2L and modify it in a better form. But it contains some information about our goal of finding optimal positions. So I'm developing homework number 4, and we'll place it on D2L very soon. And it will be less conceptual, more numerical, sitting with calculator and maybe typing few operations, but it will be not much of your time. And I invite you to visit this computer lab today. It will be less challenging than last time. We will go on slow pace, and we will practice some little optimization tasks, optimization of geometry for different systems. And if you like the style of making oral presentations, I hope you like. I like it very much. You can keep going and make next session in about a month from now, and by this time we are going to accumulate some practical skills of computing electronic structure with Gaussian software, and learning how to present and analyze it in a best way. So it would be a good topic to practice and to share our experience by this time. So on the last lecture, we were
Dr. Kilin,
yes?
I have one question regarding lab. Can I ask it right now?
Yeah, it's better now.
I was trying to make that benzene structure we discussed last time in some presentation, and the bond I tried with. I bonded every carbon atoms, and the last one was not bonding. How you make it bonded?
How you make it bonded?
Sorry. Yeah, on benzene structure, you keep on adding carbon atoms to
Uh-huh.
make benzene structure, and the last one was not bonding accurately. I don't know how to bond it.
So I think it was in the presentation of Mohammed who just showed up. So you select 2 atoms that you are not happy with bonding, and
Yeah, every carbon atom was bonding, but the last one there will be 2 bond overlapping with each other on the last
you
part,
can
right?
delete some bonds.
After deleting the bond was not. I don't know why it was not bonding,
So
and
please
when.
try to browse through other directories and just look how other
Oh,
examples look like.
okay, no problem.
Should help. Okay, so those were questions regarding practical sides. And now we are going to cover more theoretical, more algorithmical side. So on all previous theoretical lectures, we were speaking about necessity to split electrons and ions and the way to do it through Born-Oppenheimer separation. By the way, I have extended the deadlines on the D2L for homeworks. So if you even send the emails, and maybe I even graded some of the email homework, but please submit it to D2L so that it will be in an organized way. It would be a great favor to me. Thank you. So right now we are focusing on the ionic part, and we did agree that upon transition to a classical limit, which works well if the velocities or if the momentum values are small, if the masses are big, well, not infinity, but in relation to mass of an electron, then we do not need the ionic wave function. And instead of wave function, we are just playing with average positions and momenta. And the main practical question that we are going to cover, does it help us to predict the structure of realistic objects, of materials, of molecules, the interatomic distances? Okay, so it is a super brief summary of our theoretical part. So I'm removing the indices because the equations for multiple ions will be the same as for single ion and single degree of freedom. The important thing is that the increment of position depends on the value of momentum. And the momentum can also change. And the reason to change the momentum is force. And this force is can be computed in a quantum way, so derivative of the Hamiltonian in respect to position and then taking quantum average. But in many cases, we can speak about it as already having ready potential energy surface. It does depend on positions, and we just take the time derivative of it. So this potential energy surface can be calculated exactly from electronic Schrödinger equation, electronic part of molecular Schrödinger equation. Or someone can solve it for typical specific cases for specific atoms and specific interatomic distances and create a table of typical forces. And when this electronic part is not solved again and again, but one uses some tables, some parameterization from previous calculations, this is often referred to as force field or molecular mechanics method. I'm going to cover it again. So if you are running Gaussian and select the simplest possible way, molecular mechanics, Gaussian is not solving electronic part. It uses some stored data from previous generations of computational chemists. Okay. 2 equations is too much. We're going to live an easy life. Can we do 1 instead of 2? So if we apply derivative to the first one and then plug in the result into the second one, then where would it type it there. So if we apply another derivative to the first equation, we get a second derivative on the left part and first derivative of momentum on the right part. But here we immediately realize that we already have an equation for this increment of momentum, and we can plug it in. Right? So there is no actual science behind it. It is manipulation with formulas to make it comfortable for practical solutions. So after plugging it in, so we have the second derivative of position, which depends on the force acting on the ion. Do you know any artistic name for this equation? Do you recall anything in your previous experience? Yes, perfect. Can you switch on microphone and tell us once again?
The Newton's second law.
Yeah, perfect. Thank you very much. So it's Newton second law. So the reason for a particle to change its velocity is the force that one applies to it. It was known for several centuries, but now we are going to utilize this knowledge in a positive sense. And this force, we can we can use our potential energy surface, which is either coming from electronic part of our equations. We can solve and find this potential energy surface, or take it from parameterization, and then we look onto derivative of our potential in respect to position of ion. So the force is derivative of energy in respect to position, right? It doesn't surprise you. And this opens a door to go forward, to browse through this energy landscape and find the better way to minimum. So there will be substantial practical challenges that expand necessary computational time. I'm going to speak about it in 2 minutes. But since we are in the computational chemistry class, since we are trying to understand how codes are working, the codes do not operate mathematical concepts and formulas. They operate numbers. So if one has a derivative somewhere in numerical code, it will be finite differences. If anywhere we have forces or this derivative of force in position of energy in position in respect to position, which is also referred to with the word gradient, especially if it is a multi-dimensional, then one can replace it in the finite differences, so that one does have several two positions and finds values of the potential energy surface at these positions. And by dividing this difference by this difference, one is obtaining a force. And this force is something that prompts us in which direction to optimize the geometry, which bond to expand or contract. Well, this term is referred to as acceleration, and if we are going to solve our Newton second law, we are going to integrate it, right? So it is a second order differential equation. It is not too challenging. We just integrate it 2 times, right? And by integrating this equation, one can obtain, as a result of solution, one can obtain the new position based on previous position. So it is a new position after time interval t. This is position, original position, before we started solving this equation. And here, since there are 2, each integration adds free constant, right? As you happily acquired it in calculus, right? And integrating this equation, one gets 1 free constant as a initial value of momentum and the value of the force or gradient. And this one is proportional to linear. It is linear in time, and this is quadratic in time. So if you were practicing high school physics, you know that free falling mouse is expanding in time as minus free falling acceleration times squared over 2, right? Acceleration times square over 2. So it is anything moving with constant acceleration. So same thing is here. So this one is acceleration, and this is t squared over 2. So force, here it is just gravitational force, it accelerates something. And if we have interatomic distances, their combined Coulomb plus all these accumulated electronic interactions make ions to either contract or repel each other. And this force, this acceleration, makes them to change interatomic distances. And if they also were having some velocity, it will also affect where the new position will be. For simplicity, we can avoid this term for the geometry optimization task. At the end of the course, we will return to so-called molecular dynamics to simulate high temperature limit. And then we will return back to this kinetic term, but now we do not need it. Okay, there is a little trick. Since objects may experience friction, since the ions interact not only with their nearest neighbors, but also to the rest of other ions. It is physical reason, scientific reason, and practical reason. One wants to avoid several undesired effects, such as artificial oscillations. One often adds a damping parameter in this equation, some parameter, and then the remaining, the resulting equation is main equation that operates finding the optimal geometry. So it is the main equation to optimize geometry. Okay. So here I have copy-pasted one of the images of potential energy surfaces, which is 2-dimensional in this cartoon. And potential energy surfaces may have several features. And, if we are looking to complicated cases, we may need to take into account all of them. So there are possible maxima, there are possible several minima. Also, it is not shown here, there could be a dissociative part of the potential. And also there is a typical feature between which one can see in reactions between reactant and product. There is a typical barrier that comes through saddle point. For example, this could be reactant, this could be product. This saddle point can correspond to a barrier. So the geometry optimizations, meaning, well, people implies under the term geometry optimization the problem of finding the global minimum. So if there is no dissociation, then one just finds the minimal point on the whole potential energy surface. And for most cases, one refers to geometry optimization for ground state, ground electronic state, although it is possible for excited states too. Yes, Mohammed? Yes? No. Yes? No. It is the lowest one. Global lowest one. And you know, in organic chemistry, in amorphous materials, in really big molecules, there are several positions which provide local minima. And there are several options that come out of the reactions. There are several products, and typically they are several local minima which are very close in energy. If there are several minima, it corresponds that reaction will have several products. Yes, correct. Okay, so how to solve for this task? How to find such position of R1, R1 and R2 that will provide the minimum of the energy? Okay, so the first thing that comes to the mind is to explore potential energy surface at each possible interatomic distances, at each possible values. So we tweak the distance between atoms. If it is a hydrogen atom, we just scan possible distance between those two hydrogens. If it is a water molecule, we tweak the distance from one hydrogen to oxygen, from another hydrogen to oxygen, and then we try several values of this angle. And then we find the value of total energy for each of those realizations, for each of those nuclear configurations. Then we have a long list of values, and we apply sort option, which is present in many codes. I think it is in Excel, right? There are many codes that do sorting of the data according to ascending or descending values. So it is the simplest algorithm. You just solve electronic structure for each parameter, make table, sort it, and find global minimum. We are happy. Is it? Uh, So we have some complicated multi-dimensional surface. Then we select different values of our parameters, of our atomic positions. And then for each value, we are finding the for each position, we find the value of U of R1, R2. So we will have each position, we will have different values. We are mapping our multidimensional curve and representing it as a set of data. And then we take all these numerical values for this data and sort. And by sorting, we can find the one that provides minimum. Maybe it will be this one. And then we have found minimum and can go to the next chapter. Is it practical? Is it helpful? Well, if you are talking about few atoms, it is really good idea. And people were trying to parameterize the potential energy surfaces for small molecules. But here, let's illustrate this procedure, how many grid points we need to explore. So if you have only 2 atoms, it is H2 molecule, we can be practical and say that we will try 10 different distances between hydrogens. A little closer, a little further. Those different distances, we will call them grid points. Grid points. So there is 1 degree of freedom for H2 molecule, and there are 10 grid points. We can find value of potential energy surface for each of those points and find minimum. That's fine. If we are going to 3 atoms, like water, the total number of degrees of freedom is 9, but we remove 3 translational when everything moves coherently, and we remove 3 rotations and have 3 degrees of freedom. Then our dimensionality of parameter space becomes 10 to the power 3, because we have 10 grid points in for one for interatomic distance, 10 grid points for another one, and 10 for different angles. And then we need to multiply, so we have total 1,000 of realization, 1,000 nuclear configurations that we need to explore and then sort. Okay, we can do it. It is not a big deal. Let's add another atom, maybe this C2H2 molecule. Then we have, you know this formula, 3n minus 6 for number of degrees of freedom. We have 6 degrees of freedom. I even do not want to plot it. So it will give 1, 2, 3, 4, 5, 6 zeros, right? So a million of possible nuclear configurations that we want to explore if we are interested in restoring the shape of this potential energy surface. This is a little more complicated, but with good computers it is also possible. But as soon as we add for 5 atoms, maybe methanol, we have 9, so a billion points, the space of billion grid points. And as soon as we add 1 more atom, the space in which we perform the search expands substantially. So the finding the whole potential energy surface in numerical form and browsing it through available data is too expensive. It can be done if it is justified, if there are some complicated profile, like several minima, and one needs to find best connection barriers between them. But practically, one tries to make everything possible to avoid exploring the whole potential energy surface. Is there any smarter, any advanced procedure that allows us to find minimum by exploring only few configurations. We want to find minimum potential energy surface by exploring only few nuclear configurations. Is it possible? Can we do it? I hope so. So our no, for anything, for a really big molecule. If we avoid if you avoid solving electronic part, if we do have parameters for like carbons, nitrogens, oxygens, one can do systems of million molecules. So molecular mechanics is really powerful, and it is being explored in pharmaceutical industry to predict in biological, just in biology, docking of proteins when they approach each other from different sides. One does it very successfully with molecular mechanics. So, but there one does a bypass, a trick. One avoids plotting the whole potential energy surface because the dimension of this is incredible. So we take our main equation and break it into pieces. It is a very simple equation, but we want to simplify it even further. So the idea is that we break it onto simple algorithmic pieces that follow one after another, and then we repeat them in a cycle. And this cycle corresponds to navigation in the space of these parameters of interatomic distances. So we take one position, explore it a little bit, then we decide which next position we need to explore. Jump to this position, look around, and find next point. Same as we have a map, we have a compass, and we navigate in the area where we never been before. So we do small steps and look on the map and on the compass. So how do we break this equation onto pieces? So we will have several steps that are repeated continuously, again and again. Same steps repeated in a procedure. So at each step, we need to know the actual, step number I, we need actual current present position of present nuclear configuration. Then we need to know the present value of the potential energy surface. Then we need to know the increment of energy. So comparing the present value and the value that was before, or the next value, the value that was that is present. I missed delta R, just the increment of position, and then we do a simple step. We find the ratio of increment of energy to increment of position. And this ratio of increments, it can be called force, right? It is a force. And practically, it prompts us the direction where to navigate after. In one dimension, the direction means only to the left or to the right. But if it is a multidimensional, it just shows the vector where to go. And for actual value for this increment, where to go, we are applying finally our formula. it does prompt direction. Where go? And then after we have this delta R, we are going to the next step and repeating them again and again. So this simple, I wouldn't say magic because it is like really simple formula. The gradient will, if you follow the gradient direction, which each step we will approach closer and closer to the minimum, at least to a local minimum. And now we may want to write an algorithm to, well, we are not going to develop a code, but we can imagine that we need to develop a code and imagine which steps code developers are putting in to address this set of subsequent equations. Steps made by a programmer. Okay, if we are not going to actually write a code, but we want to make a plan of how to write a code, we are going to use the language of flowcharts. And if anyone in the audience was taking classes in programming, I believe that it is what's happening there at the initial stages. One makes those flowcharts, discussing them, planning them, and only then starting to implement into the actual coding. And this was designed like half a century ago, even before, when people started making programs. And the reason for those flowcharts is that programming language can change from year to year, from decade to decade, but the principle, the algorithm can stay the same. So there are very little, the dictionary is short. There are not too many operations in the programming. There is a input and output of data. You feed something into computer, you take something out. You are tracing the data going from one variable to another variable, or from one carrier of data to another carrier of data. And then there are some math operations. I don't know, adding something, subtracting something, making some functions like sine and cosine. And then there, which is represented by a square block. And then there is a condition, decision, branching, when the computer is following the will of a human, should go either one way or another way in processing data in with one formula or another formula. And this is typically reflected in this agreement of flowing charts with the diamond symbol, which has like 1 in, 2 out. If some condition is fulfilled, one goes one way. If not, it goes another way. So we are going to use this flow chart to represent algorithm finding optimal geometry. Okay. I spent half an hour drawing it this morning. So most important for a simple user, if you're not interested what is inside, we need to know what we put as an input and what we get as an output. So as an input, we need to provide initial geometry at initial step. And it is exactly what we do when we are practicing the building of atomic models. Atomic model. As an output, we are obtaining geometry that is supposed to be perfect, is supposed to represent the real world. Excellent. Excellent geometry. Or maybe excellent is not humble enough, we will say optimal. So it is what comes in and what we are taking out. So as a minimal requirement, we already know this flowchart. Throw geometry in, get geometry out. And also we can get the optimal geometry. So the value of total energy at the minimum of this potential energy surface. Okay, so how do we get to this point? So we do have set of equations that we were taken from Newton's equation. We were breaking it into pieces. And we are doing them one after another. Here, there, and then we do have a repetition of this operation. I was reading an anecdote about a programmer. When a programmer is not coming to the work, and the colleagues and the boss starting to worry where he is and send somewhere to check at home. So people come to the home of a programmer after like 3 days and find he's very tired, very cold, face is almost blue. He's sitting in a tub, holding a shampoo bottle, and reading it with a crazy watch. And then what is with you? And he just shows there. Apply shampoo to your head, wash it with water, repeat. So evidently he was repeating it again and again for 3 days. So we do not want our code to go this way. We want our repetition to stop at some point. And therefore we put these diamonds. We put these decision points. So we, just in case our program was designed in a stupid way, we can start at the very beginning saying that if repetitions occurs more than 10 steps, if it is more than 10 steps, then everything fails. Then it is a bad program. We do not want to use it, and we fail to find the geometry. So it should work well in a reasonably small number of steps. Okay, so it is a breaker just in case protection of stupid program. Then we have another branching point that will be a criterion of success. So since it is a numerical solution of all problems, numerical finding of the minimum of the potential energy surface, we will never get exact, absolutely precise position of this minimum. It will be always a little bit off. So what we can control is how far off it is. How far off? So we want to compare our increment of energy with some predefined tolerance limit. This tolerance means that we set up the value that we allow our numerical experiment, the amount of error that we permit to be there. So if we really need something precise, we just set up this parameter very small. if we are in a rush, we can set up it a little bigger. And if this criterion, if at the one of the subsequent steps this criterion is met, yes, then we report optimal geometry. Then the code stores it as a file or shows it in a Gauss view as a nice image, and then code is completely completed. So what if we are not yet, if we do not meet the success criterion? Then we need to repeat the procedure. So finally we get to the actual procedure. What do we do here? So before, at the very beginning, we should have value of the potential energy surface where we start. And then here we find the vector of motion. So it helps us to navigate. So which increment, and in multidimensional it is a vector, in which direction we should go to chase, to follow the minimum of potential energy surface. And we computed by this ratio of increments of energy and position. So this ratio prompts us which way to go. Okay, then we take this prompt and add it to the present position. So we stay somewhere, the compass shows us where to go, and we make next step in this direction. So we make an increment in position. And then when we are at a new point, we recompute the value of energy at new point. Because later we need it as for difference, or for gradient, and also for criterion of success. Okay, then we check if our new position will give us success. If not, we go forward. So we take this gradient, take next increment, next vector of motion, jump to next position, compute energy, and check whether it fits our success criterion. And then we navigate in this space of nuclear configurations. Some programs even display it. So you look at a molecule and it starts dancing and trying different configurations, and finally it finds something really reasonable. But since this procedure is very quick, sometimes it is not, the intermediate steps are not displayed. You see only initial and final values. Any question about the algorithm? Okay, no. Okay, can we apply this algorithm? Can we check that it is working? Can we illustrate it? Well, let's apply this algorithm to the simplest possible problem. So let's consider one-dimensional potential energy surface. And let's consider the potential energy surface that is known to us. So we take something that is already known and just apply the method to see that it works. So let's take just as a mathematical game. Take potential energy surface is equals to r squared, right? So just a parabola. And we know that the minimum will be at r equals 0. But let's check if we can find this r equals 0 by algorithmic procedure. Is it possible to answer this problem not in a mathematical way of finding the minimum of derivative or inspecting the function, but just following the algorithm? And the reason is that this really simple. very unsophisticated algorithm can be applied to multidimensional procedures when nothing else works. So we are just testing it on simplest example. We provide a little motivation. Why we are doing this strange task? Since for many dimensions, nothing else works. Okay, so here is our potential energy surface, and it is an answer that we want to get. So we want to achieve this answer by this procedure. So we are going to pretend that we are computers and follow this algorithm ourselves. So I will try to do it myself here in class, and homework number 4 will be the same game for you, trying to pretend that you are computers. So just following everything that was before, we set up initial position arbitrary. Here, let's take -5. For homework, it will be maybe +5 or something else. Then we set up some tolerance limit, the amount of error that we permit our procedure to exhibit. So if our energy will be minimal with precise up to 0.3, we'll say, okay, stop, we are happy. And then we need to have some initial increment. And in one-dimensional case, this vector, this direction of motion, means only the how far and left or right. It is really simple. As soon as we get more than one, it will be multidimensional vector that is not possible to do by hand. And then there are some other parameters. This time step, and this gamma parameter that helps to find this position quicker. Okay. So at the very beginning step, we have our position at -5. Then we know that -5 squared will be 25. Okay. And it is too early to do those things, because for delta or increment we need at least 2 positions, 2 nuclear configurations. Okay, 25. Step number 1. Since we set up this initial delta R 1, then we are getting new position at step 1, -4, right? -5 plus 1 equals -4. And then we take 4 squared equals 16. Now we can subtract those two and get this delta, which will be recent minus previous will be -9, right? Okay, good. And now we have our delta R equals 1 and delta U equals -9. So we just divide them by each other. -9 divided by 1 and minus sign, +9. Okay. Then we have some just parameters for time step, which is right now we are not related to any time, but we need those to apply the Newton mechanics. So we set up the delta t so that delta t squared over 2 will be 1. And then we are applying this formula. So delta change of energy, increment of energy, ratio to change of position with minus sign, and we also add this damping parameter. Okay, so we have this 9 times damping parameter will be 3. So it is our delta R. So what does it mean? It means that if you want to get closer to the minimum from the r equals -4, we need to make a step as long as 3 to the positive direction, which does make sense, right? So we know that we need to approach 0. We need -4 plus 3. Then we are getting -1. It will be our next step in our nuclear configuration of this irrelevant abstract potential energy surface. No, it's wrong. -1. Yes. -1. Then -1 squared. We just apply this formula. It will be 1. And then we apply recent minus previous. So this 1 minus -16 will be -15. And then we compute new gradient. So it will be this -15 divided by the increment of the position. And we are going to get gradient. -15 divided by 3 should be, and with minus should be 5. Yes. Okay, so this 5 is our gradient. And then we have same parameters for time. And now we are computing our next increment. How far should we go? Increment. So this is this gamma parameter, 1/3, and then this one is gradient. So we divide 5 by 3 and get something 1.6 blah blah blah. So it is our next increment. So according to our algorithm, if we are at point -1 and we want to approach minimum, we should step in the positive direction by as far as 1.66. Well, we are definitely missing the correct answer, but it is a stupid algorithm. It is short and simple. At least we are not going to 100 or whatever. It is one of the danger of those algorithms. So, there are several dangers. One, it can go across the barrier, go too far, and just go to dissociation. Another, it can approach approach the minimum too slow. And the third challenge is that it can set up artificial oscillations when it will not get to the right minimum immediately, but will try to jump across several times. Too far, too close, too far, too close. And if the algorithm is designed in a good way, then this amount of this wiggling about the correct answer will be smaller and smaller. So what we are going to experience with this algorithm from now on, it will be just a little further than 0 and a little bit lesser than 0. So with -1 plus this new delta r, we are going to 0.66. Let's check if we are getting closer to the answer, if we are getting closer to the minimum in our criterion of success. Here is 0.66 squared. And following this line of data, it looks, well, not perfect, but promising. So we see our original value was 25, 16, 1.4. So we are getting to smaller and smaller energy. So we are approaching the minimum. The algorithm has some limited value to us. So let's see what is the criterion of success. So we take present value, 0.4 something, minus previous value, 1. So we get minus 0.5 something. Okay, here it is also good sign. So the convergence criterion was minus 9, then it went minus 15, then it goes to much smaller value. So later we will observe how computer is doing it, and when those convergence criteria get smaller and smaller and smaller, it is a good sign, meaning that probably we are using the right code, or we are using the right setup of the code. Okay, now let's use this information to find the ratio and proceed with gradient. So this 0.5 divided by this increment will be the gradient. So here is an interesting thing. The gradient became smaller than it was before, and another thing that it changed the sign. So although it is a very stupid, very silly algorithm, it recognizes that we went away from the minimum and we need to turn around and return to actual position. So here these were positive, it means go forward. Positive means go forward. And here it is negative, meaning that algorithm saying yes, yes, hey, you are too far, return back. So the algorithm corrects its own mistakes, which is good. And now we are applying this gradient, multiplying it by a damping parameter, and get a new increment. We see that this new increment is much smaller than the increments before. So it is minus 0.1 something. So we went too far in this 0.66, and we go back by 0.1. Well, it is not perfect, but we are approaching 0. At least we see it that 0.5 is closer to 0 than 0.6. And now we can take this 0.5 squared, find the present value of our potential energy surface, and subtract the previous value, which was this much, minus this value. 0.4 minus is almost 0.3. Oh, 0.3 minus 0.4 will be minus 0.1. Okay, so this minus 0.1 is already smaller than our predefined tolerance limit that we agreed before starting this game, that if the difference in energy will become smaller than 0.3, then we will say, okay, we are happy, we are stopping procedure, and we are reporting success. Of course, it is a not perfect success, not ideal mathematical precise value, but we, from being very far, we are coming closer to the minimum in pretty small amount of steps. So we are applying this diamond branching in our algorithm. We are comparing that this 0.136 is smaller than 0.3 in absolute value, and we are stopping the algorithm. Saying, okay, great, stop. Report to the user what we have found. Okay, and we are reporting that we have, with this precision, we have found that optimal geometry of our unknown potential energy surface is when position is equal 0.547. So it is a little bit off compared to 0, but it is what we know it as people who give task to this algorithm. But if it is an unknown function, it is not bad result with this precision. So the optimal geometry is at nuclear configuration corresponding to distance 0.54, and the minimal energy is 0.29. Okay, but all these results are trustable up to this precision. So our optimal energy is even smaller than this precision. So regarding the algorithm, we are happy. If you want to get better precision, we just need to set up smaller tolerance limit and keep going. And then it will jump to the left and to the right of minimum and approach it. And finally, we will get as high precision as we need. 5 sig figs, 10 sig figs, it's just a matter of number of steps. So our algorithm gives some positive knowledge. It shows that it does work. And it illustrates how the computer codes are getting from very crazy, from very irrelevant geometry to something that is much more closer to the optimal geometry. Okay, I think we did a big effort. Let's meet if you are able at the Arts and Science basement and try optimizing some molecules, maybe even materials. Okay, it is the end of lecture. Class is dismissed. If anyone wants to ask questions, I will stay here and wait.
Excuse me, Dr. Gillen.
Yes, please.
What will be in today's lab? Can you briefly explain us so that
Pardon
we
me?
can? What will be in today's lab? Can you
Today
explain it a little bit so that we can?
we will have several atomic models, and we will record geometry before optimization, then optimize and record geometry parameters after optimization, like interatomic distances, angles, and have an illustration how geometry optimization works in practice. So when we met last time, we were learning practical steps. Now we are learning consequences. Like what positive knowledge can we get out of geometry optimization? Okay.
We're not sure how to follow up your labs. Actually, we're not. Like,
I will try to forward you the directory where I give examples. Probably it is the best way.
okay. Okay.
And you can just go to this directory, open files, and look on them.
Is there video recording on that lab or no?
No, there is no video equipment in the lab.
Oh, okay, no problem.
Maybe if the course will be taught next time, we'll set up a video recording in the lab.
Thank you.